the U substitution stuff. We've got a new technique to get into today. It's not going to feel like it at the beginning, right? But then U substitution didn't feel that easy at the beginning. It's just different. It's just different. Now, if when you take count 2, when you take count 2, okay. For those of you that take count 2, the antiderivatives you would learn how, and most books don't. Remember how I said that integral and antiderivative are really not the same thing? It depends what integral you're talking about. If you're talking about an indefinite integral, then that is antiderivative, right? And so most calculus professors, especially, old people like me, and from back in the day, most books will call it integration techniques. Now, really what it is antiderivative techniques. Or you could say indefinite integral techniques, okay? But it involves the antiderivative. Now, the first would be your basic antiderivative. So those like page 333, power rule, antiderivative sine, cosine, e to the x, whatever. Those kind of just basic antiderivative techniques. You might have to kick out at 1/4 or something like that. You have to do some algebra. Like, for example, we talked about if you had x minus 3 over x squared, right? You should split that apart, and then it would just be, that would just be 1 over x minus 3x to the negative 2. Now, why did I not write this one as x to the negative 1? Because it's an ln x, and it's easier to see if you just write 1 over x. But otherwise, 3 over x squared, it's easier to write it that way because you're going to do a power rule, right? So this would be ln x, this would be a power rule. But that would be what I call a basic antiderivative. You might have to do some algebra rearranging first, but it would be just one of your basic antiderivatives. Then the next one you typically would learn would be U substitution. That's your chain rule. That's anytime you have some stuff on the inside, although we've learned some other things to do. Sometimes we let U be the bottom, right? But usually it's the inside of a function because it comes from the chain rule. And a lot of functions are that way. So this one is a pretty common technique that needs to be done because you think about it, most functions have some stuff on the inside. And so, therefore, when we do derivatives, it was probably the most common rule we used in derivatives was the chain rule. We almost always seem to have to multiply by the derivative of the inside. So, U substitution is pretty common. The one we're going to learn today is called integration by parts. Okay, now it comes from the product rule, and we'll talk about when it's used and how you can kind of recognize when it needs to be used. But that is a big thing when you get into Calc 2 and you learn all these different techniques. You've got to not only know how to do the technique, but you've got to be able to identify which one is necessary to be used. It's not like they're options. It's not like, well, maybe I'll just use integration by parts on this one. Or I'll use U substitution. No, I mean, there's one that can be used, and that's it. Okay, you don't have you pick your favorite, kind of thing. It's not like there's 3 different ways we could do this one. It's typically not that way. Then there's one called the method of partial fractions, and that one's used in, as it says, in fractional ones with rational type functions where you've got, kind of things like this, except ones that aren't easily split up with algebra or something, so you do this. There's another one that involves trig functions called trig substitution, and there's a couple more, and the names are escaping me right now. So we're just going to do these. Now, on the actual AP test, so on our final, in our packets, you'll really only see these 2. Okay, integration by parts will be on it. Okay, so it'll be on our gateway test, but that'll be it. Okay, you won't be seeing it other places. But when you see it next year, if you take Calc 2, or the year after, or whenever you take it in college, possibly, you'll have seen it. And you'll have a head start on it a little bit. Okay, all right. So those are the ones we're going to do. Those are the techniques we'll know on our gateway test. There'll probably be a few that are here. Most of them, you know, I would say 2 to 3 will be in this category. 5 to 6 will probably be in this category. 1 to 3 of them probably in this category. Okay? So depending how it all shakes out. So you're going to need to be able to do, you know, some of each of them. Okay? All right. So let's talk about, let's finish up here. Now, we'll still continue to practice U substitution. You still ask questions about it and so forth. They'll still be part of the homework each day. So it's not like we're finishing U substitution, but we are going to move in and talk about this one today. So let's do some U substitution. Which one do you want to look at?
24.
Which one?
24.
Okay, what is that one? Is that in the packet? Okay, what is it?
1 over 2 root x.
Like that?
Yep.
Okay, so one of the things I said yesterday was it's quite common to get into a routine of, okay, doing a U substitution, doing a U substitution, doing a U substitution. This could happen on a gateway test. We were just talking about how you got these 3 different ones. You got to identify which one you need to use. And you get into this kind of this routine of doing a certain way, and you get locked into that. You kind of get focused. And so, Joe, you see it already?
Yeah, this one's easy.
So, what are you saying?
You don't need U substitution.
You don't need U substitution. This is just 1/2, and this is x to the negative 1/2. And so this is just a power rule. So you raise that up to 1/2, you divide by 1/2, which would cancel this. This is just square root of x plus c. I don't care if you leave it like that or like that. So that isn't even a U substitution problem. Okay? But it's really easy to get laser focused on that. Remember, typically U substitutions let you be the bottom, I think you could do a U substitution here. I mean, let's look at it. Let me see if somebody let the U be the 2 square root of x, let's say. What would that be, 2x to 1/2? So the du would be x to the negative 1/2 dx, is that right? Which would be 1 over square root of x dx, right? And isn't that setting right there?
But you change your U is to. You don't have.
I'm with it. I'm with you, but hang on here a minute. Okay, you're right. I could put a U down here, but that would be the hard part about doing U substitution here is you would want to do what you normally do is you're like, well, this is U, so you'd really want to make that be your U, wouldn't you? You'd want to make that be your U, but then you got this dx that you don't have anything with. Let me show you a couple different things you could do here. So the one I'm noticing is right here I see this, right? And I see that that's equal to that, right? So I could take that out and put dx there, right? No, not dx, du, right? So I can put du there. Now what am I left with? So can I just put that there? And then, or in there, what would I put in here? No, nothing, because everything else is, I've already subbed out everything, right? The 1/2 I just brought down, this is my du, so I don't even need u in there. And I could put a 1, or I could leave the 1/2 in there. Now what's the antiderivative of 1? So isn't this 1/2 u plus c? And what was c? Or what was u? So this is 1/2 times 2 square root of x plus c. So it did work. It did work. And, okay, so you guys were saying, oh, wait, this is your u right here. Okay, so let me do that in black. So you're like, okay, I want to put a u there. I could get that. And this 1, of course, would just be the 1. And so what am I left with? I need a dx. Now I look over here like, oh, crap, I got to solve for dx. Well, I can do that. Couldn't I move this over here?
Yeah.
Now, normally I told you don't mix x's and u's, but in this case, what did I just say that square root of x is? What is square root of x? 1/2 u. So couldn't I make this 1/2 u du like that?
Yeah.
So now couldn't I sub out that dx as 1/2 du? Or excuse me, 1/2 times u du? U's would cancel,
Same thing down.
so you get the same thing as you have down here. So actually there's 3 different ways we could have done that. 2 of them did use U substitution, but it was kind of a weird U substitution, and some things happened that we weren't used to seeing. So I'm not sure we did come out of it very good doing it. But then when you look at how much easier it would have been without doing U substitution, you feel kind of silly. So that's fine, right? That's one that happened to work, but there will be some others probably where you might try a U substitution and it just runs into a dead end and you realize I shouldn't even be using U substitution. Okay, all right, what's another one?
38 in the book.
38 in the book, what do you got?
You would have the integral negative x over the square root of 1 minus 4x. And dx.
Okay, so in the book, I said to pick like 7. Now this is going to be the key for you guys. Now some of you are going to do a good job of really practicing a bunch of problems and going through and doing those, and you're going to be in really good shape when it comes to the gateway test because you're going to have seen a lot of things, and you're going to, when you recognize one, you're going to go, oh, yeah, okay, I remember that. That was one of those in the book I did, and da-da-da-da-da. And the next 2 days, Monday and Tuesday, I'm going to ask just like this, hey, okay, so you had your assignment. A lot of the assignment's going to be, here's some problems in the packet. Here, do a bunch in the book. And then we'll go over questions. I'm not going to go through and say, hey, now make sure you can do one like this. Make sure, because I've pretty much covered with U substitution most of the things that can happen. Not very many times, but we've seen pretty much everything. Okay, now it's going to be a matter of you coming up with things that you're running into that are a problem. And if you're not practicing very many, you're not going to run into those. And then you're not going to ask about them, and I'll assume we're all good, and then we'll just, Now, I am going to pick out some to have you practice on Monday and Tuesday. I'm going to throw some up there and say, here's 3 problems, do them. And then I'll give you 10 minutes, and then we'll check them. And so we're going to do some of that review. But the ones you practice are important. Okay, so what is your thought about what you could maybe use for you here? Because it's got it inside. So as we learn this new thing, this integration by parts, right? One of the things that will tell what we should be doing is U substitution usually has some stuff on the inside. I mean, that's your first giveaway that you want to do U substitution. Okay, so what would be a thought for your U?
X.
Yeah.
Well, that would be a really good thought, but most people would not have that thought first.
Most people would think 1 minus x.
You would think 1 minus x to the 4th, right? Because that's on the inside. Now remember, we should be getting to the point where once you think about what your u is, then you should be thinking what the du will be, which will be what?
Negative 4x.
Negative 4x to the 3rd, and I don't have an x to the 3rd setting. So then the other thing you should think about is anytime you have this, you should think of, at least it should be in the conversation, you should be thinking of what? Arctangent. Whenever you got 1 plus something squared, you should be thinking of arctangent. And anytime you have this, you should be thinking arcsine. So those should at least be in the conversation. They're not always going to be arctangent or arcsine, but they should be in the conversation. Matter of fact, if this would have been an x cubed up here, then what would we have done? We'd have let u be the 1 minus x to the 4th, and it would have been a basic u substitution problem. It would not have been an arcsine. But since it's not an x cubed, turns out it is going to be an arcsine, because we're going to want to let u equal, because what is this squared? That's x squared squared. So we would want to let u be the x squared. That's going to make this 1 minus u squared, which is going to give me my arcsine look that I want. And then the double bonus of why I want to do this is because then the du is going to be 2x dx, which is setting right there. Okay? So you want to divide the 2 over because it's not really in there. And so now when we do our subbing, our x dx would come out as the 1/2 du, and then this bottom piece ends up being square root 1 minus u squared, which is just a basic arcsine. So we got 1/2 arcsine of u plus c, and then that's 1/2 arcsine of x squared. And there is no arc cosine we have to work with, because if you remember the derivative rule for arc cosine, it was the same as arc sine, but it had negative on it. So if we ever see a negative out here, we wouldn't think of that as arc cosine, we would just think of it as negative arc sine, and they are the same. And the reason negative arc sine is the same as the reason negative arc sine is the same as arc cosine and vice versa is because the additional thing that would need to be in there would be a shift. Sine and cosine are shifted angles by pi halves, right? They're just shifts. So if you do an arc sine or an arc cosine, you just add on or subtract the pi halves to them. Well, then that gets absorbed into the C. And that's why we can just trade one for the other. Even though technically arc sine and arc cosine aren't the same, they're a shift of pi halves from one another. Well, that gets taken care of with this. Okay, Spencer?
50.
Is that in the book too?
Yeah.
What do you got?
X squared over x minus 3dx. No, it's just x.
Oh, just x minus 3. Okay, now, I was thinking of this one. I'm glad you picked this one. Because this is the one that I was just talking about, that if this would have been flipped, right? If this would have been this, we would have done what? Just split it apart. This would have been what we call a basic antiderivative. But since it's flipped, and we can't split apart a bottom like that, what do we pick for our u? Right? We let u be the bottom. Okay? Because what that does for us is it gives us du would be 1 dx. We don't write the 1. And so when this all subs out, the dx comes out easily as a du. The bottom is u. Then we got this extra x squared. Well, what do we do when we have an extra x? We solved here, so we got u plus 3 equals x. Now, it's an extra x squared, but that's okay. We can make this u plus 3 squared. And then what?
Yeah, that's right. I got to there, and that's where I got stuck.
And that's pretty common that people get there and get stuck. But if you're okay with this, where we just split this apart, what can you do with this top? Just FOIL it out. See, just FOIL it out. So that's the thought process would be, oh yeah, I could split this apart if this was written out like that. Oh, but I can write it out. It'd be u squared plus 6u plus 9 all over u. So then that just splits u squared over u would be u. Notice I'm still putting my integral sign because I have not done an antiderivative yet. All I'm doing is algebra. So u squared over u is u. 6u over u is 6. And 9 over u is going to be an ln, right? So this is going to be 1/2 u squared plus 6u plus 9 ln u plus c. Okay? Then when I go to write my final answer, u was x minus 3, so I got 1/2 x minus 3 squared. I got 6 times the quantity x minus 3, and I got 9 ln x minus 3 plus c. So the blue would be my answer. Now, one comment I'd make on this problem is that when we did derivative gateway, we talked a lot about simplifying, where we had to combine some things that were simplifying. The nice thing about antiderivative gateway is you don't really have to do that. Like, for example, right here, you can distribute this and get 6 minus 18. Well, what could happen to that minus 18? Absorbed into the c, right? You could also FOIL this out. And then you'd have some x terms that would cancel with this 6x. So if you check this one on your calculator, my guess is it would FOIL this out, distribute this out, combine some of those things. The constants would get taken up with the c. And so it probably would not look like this on your calculator. But I'm okay if you stop right here. So most of the time, I can't think of too many times on the gateway test that you have to do really any simplifying at the end. You pretty much get your antiderivative, you put your x's back in, and then you pretty much can stop right there. Okay, so that's a good one. That's a good one. So it just took us one extra step here where we had to do some algebra and FOIL that. All right, good. What else? While we're on that one, you said 50. How about 51? Let me try 51. Feels like one we should just know, right? I mean, we know the derivative of tangent. But we don't. I mean, if you look at page 333, it's got the antiderivative sign, got the antiderivative cosine, it's got the antiderivative secant squared, because that's tangent, right? Now, we could do negative cosecant squared, that was cotangent, we won't get into cosecants and cotangents very much at all.
Are we gonna have to split this in cosine?
That's what I would do here. So you have two choices. Well, you do it on your calculator and then memorize it, right? You know, I mean, if it shows up on the gateway test, you're gonna have to do something, right? So if it showed up on the gateway test, you could just do it on a calculator, see what you get, and then memorize it. Because our list on 333 could have been longer, right? I could have said there's more we're gonna memorize than just these, right? And the more you do memorize, the better it is, right? Because you won't have to then do it. But yes, that's what we would do. We would split this into sine over cosine, and then do what?
Give up.
Okay. So now you gotta get 9, now you gotta get, you know, you can only miss one more. Wouldn't you do the bottom? I mean, because here's why. If you let u be the sine, the du is cosine x dx. Is there a cosine x dx setting? No, there's a 1 over cosine x dx setting in, but so that would be no good. But if you let u be cosine, then your du is going to be sine x negative, sine x dx, which is secondary. You see what I mean? So that's why you'd want to let u be the bottom. And so du would be negative sine x dx, which is setting there except for the negative, so we'll just flip the negative over there. And so now we get sine x dx would be negative du, and then we'd have 1 over u, so that's negative ln of u. So it's negative ln cosine x, which is not a hard one to memorize. And I think sometimes you'll see that written as ln secant. Why would that be ln secant? You can put the negative 1 on a log, you can put the negative 1 inside as a power, so it'd be a reciprocal of cosine, which is secant. So sometimes this is written as ln secant or negative ln cosine, either one. So now you got a choice. If you could add that to your list and just memorize that, so if you ever see you need to do the antiderivative tangent, you can just know it, or do a u substitution, write it sine over cosine, do a u substitution. Okay? All right, what else? $31. That's all? Well, if that's all, either you're really, really doing good,
Or what?
or you haven't done enough to know that you're doing really bad.
We're doing really well.
No, I said either one. I mean, it could be either one, so. But I do grade your quizzes, so that might be. No, you're doing fine. You're doing fine. Okay, what do you think on this one? What are your options? This is another good one. This is a good one, dude, because something happens in this one we haven't really seen a whole lot of. It's not a major thing, but it's
U minus 2.
Got a weird answer.
yeah. So let u be the inside, right?
Yep.
Now again, the more you do of these, you start to already think a few steps ahead. Hopefully, you're already thinking about, if I let u be that, that's just going to be a constant du. So I'm going to have an extra x sitting out there, but I can deal with that, right? We have an extra x, we solve for x, right? So this is going to look okay. It's going to be one of those. I'm going to have u to the 1/2. Probably going to have to distribute, right? So if you've done enough, that's what you start thinking ahead of time. You can kind of see where you're going to end up with on this one, okay? So at least you know you're headed down the right road, right? It's kind of like driving and you make a turn down a road you've never been before. You don't know what's going to happen, right? And that's what you were at hopefully a day or two ago. You know, now the more you do, now it's like, okay, I've been down this road before. I kind of know what I'm in for. Okay, this is going to be negative 2 dx. There's no negative 2, so I'll move it over here. Okay, and we just have that. So now when we sub, we're going to have our u to the 1/2. So that takes care of that. We got our dx, which is this and that, negative 1/2 du, and then we got that extra x. So we got to solve for it. So up here, that'd be u minus 3 equals negative 2x, right?
Yep.
Now it's all about how you write it. You can either make this really hard on yourself or a little bit easier on yourself, but it's all about the algebra, okay? So when I divide this by negative 2, I think what I would do is write it like this. Okay? I think I would write it like this. So now when I bring that over here, how would I bring it over? I would bring out this -1/2 here, and then I would have the u minus 3 in here. Otherwise, if I divide this by -2 and divide each of those pieces, now I got fractions in here, and then when I distribute, I got a whole bunch of fractions all over the place, and there's a good chance I'm going to mess something up there, multiplying that through. Otherwise, here I just have my 1/4, and now I can distribute that, so I get u to the 3/2 minus 3u to the 1/2 du, right? And now I'm ready to do the antiderivative. Again, a common mistake I see is you get so caught up in this algebra that you think you've already done the antiderivative and you take away the integral symbol and stuff, so you got to be careful of that. But now we're going to raise this up one. It's 5/2, and we're going to have 2/5, so what's 1/4 times 2/5? That's 2/20. Remember, you just multiply across, which is 1/10. We should simplify that, so that's u to the 5/2. And then raise that up to 3/2, that'd be 2/3, so I got 3 times 2/3 times 1/4, because I have to distribute that 1/4. You can do it later, you can do 1/4 when you're done. So those cancel, 2/4 is 1/2, u to the 3/2 plus c, and then put your 3 minus 2x back.
What happens if we forget to put our u back there?
It's wrong.
It's garbage.
Now, I will, especially in the first one, right? To get 30 out of 30, we talk about derivative, you got to earn it. So you can't make sure to do that. If you're on your 5th one, and that's the difference between an 8 and a 7, then I might let it slide. Okay?
So you let it slide?
And I'll remind you, I'm going to probably, while you're taking the gateway, I'm going to probably say, don't forget your plus C's, right? And don't forget to put them back in terms of X when you're done. Okay? All right. Good one. What else?
Just pick a random one.
Oh, I have
It was 29. I didn't do it, but we can do it.
How come you keep picking ones you don't even need to do U substitution? You hadn't even looked at it.
Nope.
What about 52? The very last problem.
Which one did you say? 52? Okay, that's what we're doing. Secant X but you see, and right now you guys are kind of getting in the mode of you're just kind of guessing, you're just kind of looking at ones and saying, hey, so, which is okay right now, but by Monday, right, part of your assignment is going to be to do a whole bunch more of these plus this new thing we're learning and come up with some that you've actually tried and thought about, and then what'd you run into. There's 2 routes we can do on this one.
Let's do algebra before.
On this one, what do you mean by algebra?
You could put it as sine over cosine.
Sines and cosines. Okay, so that is definitely an option. Okay? In this one, it's going to turn out to be the longer option. That's okay, because like I said, you're driving and you got a couple of paths to choose and you haven't been down this road before, so you don't know which one's the longer one. If they'll both get you there, who cares, right? You take the longer one, it's fine. So we could rewrite this as 1 over cosine and sine over cosine. So this is sine x over cosine squared x dx, right?
Just drop the intervals.
What do you think?
You just do cosine X.
Let u be the bottom inside, right? Because there's an inside there. And again, you're thinking, and the nice thing about that is the du is going to be sine, negative sign, but and that's setting right up on top. So anytime you get a sine over cosine kind of thing, you can do just like we did with tangent. You can let u be that sine or cosine that's in the bottom, and that usually will take care of the top. So let's see where we go here with this. Is negative sine x dx. Some of you maybe are already saying that there would have been something a lot easier here, and that's fine. But there's our sine x dx. So that's just our negative and our du. then this is 1 over u squared, but that would be better written as u to the negative 2. So we raise that up 1 is negative 1. Divide by negative 1. We'll cancel that. This is just u to the negative 1, which is 1 over u, which is 1 over cosine. So this is 1 over cosine x plus c, which is the same as secant x plus c. And then some of you again may have been thinking, oh, I remember on my derivative rule sheet that the derivative of secant is what? The derivative of well, it better be. The derivative of secant better be secant x tangent x. That's what it is. If you go back to your derivative rule sheet, the derivative of secant x is secant x tangent x. So if you remembered your derivative rules, when you saw this, you should have been able to just write the answer. Right? You should have been able to say, oh, the derivative of secant x tangent x, so the antiderivative of secant x tangent x is just secant x. Now, it's okay because you got away with it, right, in that one. Now, there is one that somebody in the other class asked about, is 54. So look at 54. Okay? So on 54, what would your first thought be there?
Put u in greater than 1 plus.
You would go to the inside and you'd let u be 1 plus secant x. Right? Problem with that is, the problem could be, like we just talked about, you don't know the derivative of secant x. And turning this one into sines and cosines isn't a very good strategy. It's messy and it doesn't really work very well. So you do need to know the derivative rules that we learned for the last gateway test. Now, I'm not saying secant's going to show up a ton or maybe at all, but it could. So you better look over that page we had of derivative rules. Because on this one, you're going to need to know that the derivative of secant is secant x tangent x, and that's what makes this actually a really easy one. Because that secant x tangent x is just sitting right there. So this whole thing's just going to end up being u to the 1/2. Right? So it'll be a simple. Okay? But you had to know that the derivative of what the derivative of secant was. Okay? Not one of those we run into very often. So it is harder to memorize. So you should look back at those. All right, let's go ahead and talk about our next thing, the next technique we have. So what happens if you get a function that came from some derivative that was not a chain rule kind of thing? For example, maybe a product rule. Okay? Now, one that comes from, say, a quotient rule is going to be messier. That's where you're probably going to get into your partial fractions, some of these other techniques we've talked about, some different trig ones where you have to do some trig substitutions, okay, those kind of things. But we're going to focus on integration by parts. Integration by parts comes from the product rule. Integration by parts deals with problems that would have come probably from a product rule, okay? Now, it doesn't mean they're going to look like products. Matter of fact, if you look at U substitution is products a lot of times. Because think about it, U substitution comes from the chain rule, which what do you usually do? You do the derivative of the inside, or outside, leave the inside alone, times the derivative of the inside. So a U substitution almost always looks like kind of a product also. So just because it looks like a product doesn't mean it's from the product, all right? But these are going to look mostly, the ones we do, we're going to stick with fairly simple ones. You get to an Algebra 2 class, you get some a little harder, but we're going to stick with ones that typically look pretty much the same. And I'll show you what that is here when we get ready. All right, so here's the product rule. Now, I don't care if you write this down or not. We're going to develop the formula. It really is a formula. You know, U substitution is more of a technique. You're going to pick a U. And how do you pick the U? Well, kind of what's on the inside, whatever will give you good DU, that kind of thing. But the point of integration by parts, actually the point of all of these techniques is the same. Turn our integral that we're trying to do into a new integral that's easier, right? Isn't that what U substitution is all about? We got an integral with x's, we turn it into a new one with u's, which is easier to do. Well, that's the end result of integration by parts also. We're going to turn our original integral into a new integral that is easier to do, okay? All right, so I'm going to show you, there's actually kind of a formula that we follow on this one. So here's your basic product rule right here. So first I'm going to do the antiderivative of both sides. Now what would I get on the left if I do the antiderivative with respect to x? Won't I just get u times v? Because it'll be the antiderivative of the derivative. They'll cancel each other out. So I'll just get u times v. And on this side, I'll just write the integral with respect to x, which is what that means to do the antiderivative, right? So I'm just going to do the antiderivative of both sides of this. So I get that right there. Okay? Hopefully that makes sense.
Sure.
All right? Now, I'm going to rewrite the u prime and the v prime because whenever we do integrals, we don't like that notation. Instead of u prime, we'd rather have what? Du over dx. And instead of v prime, we'd rather have dv over dx. Okay? So I'm going to do that. So this would look like that, right? I just changed my u prime into that notation, changed my v prime into that notation. Now you probably see what's going to happen, right? It looks like dx's are going to maybe cancel out. Right? And that is what's going to happen. What I'm going to do in my next step is I'm just going to split this. Now you could say, can you distribute that dx? Yeah, technically that's kind of what's happening. But we also know that when we had two things added together in an integral, we could split it into two separate integrals. So I'm going to actually write it that way. So I'm going to go ahead and split it into just two separate integrals. Okay? So left side I haven't touched. Right side, I just put it into two separate integrals. Of course, each integral has to have its own dx on it, right? We know that. And so it seems reasonable that we could do that. And it's true, you can. Now, you could argue, but is that dx that's sitting there really multiplication? Is du over dx really division? Well, that is where it comes from, right? Du over dx comes from the idea of slope, changing u over changing x. This actually does come from a multiplication kind of situation. It's what we're going to study later in chapter 5. So, yes, bottom line is we can do that. So now the v and the du are kind of backwards from what we normally see, so I'm going to flip those around. So we end up with that, right? So each step, hopefully along the way, kind of makes sense, seems reasonable. And then what I'm going to do is I'm going to take this integral here, and I'm going to subtract it over to that side. Okay? That you're not buying. So I'm just going to subtract this integral over to here. All right. And that's actually our final step. Now, when I rewrite it and actually write it for me, I'm going to flip it around. I'm going to take this and bring it over here to the left. I'm going to take this and I'm going to put it over on the right. And that's going to end up being our formula. And that you do want to write down. Okay? So as you're writing that, just explain what this is about then. So the integral on the left is going to represent our original integral. That's the integral we're trying to solve. Okay? What we're going to do is we're going to rewrite it using this formula. In other words, we're going to trade that integral for a new integral that will hopefully be easier to solve. That's the idea. Okay, so just like u substitution takes our original integral, rewrites it as a new integral that's easier to solve, that's what integration by parts is going to do. Okay, now, to be able to do that, we're going to have to take, and this is why it's called integration by parts, we're going to have to take our integral we're given and split it into two parts. Part of it's going to be, we're going to call u, and part of it we're going to call dv. Now, the part that has dx on it is always going to go with the dv part. Okay? So part of the integral is going to be u. So we're going to split it into two parts. One part's going to be u, one part's going to be dv. Now, once we know which part is u, so it's kind of like u substitution because we're going to pick something for our u. But it's going to be a little more cut and dried what we pick for our u. Okay? So we're going to pick part of it to be the u. And from the u, we can always get what? Du. By doing what? The derivative. Because we're going to need du right there. Right? And then we'll need the u right there. And then the leftover part, whatever part we don't pick for the u, that'll be our dv part. Well, we don't need dv over there anywhere, but we do need v. Well, from dv, how can we get v? Wouldn't that be the antiderivative? From dv to get v, you would do the antiderivative. And then we'll take that and put it there and there. And then hopefully that will give us an integral that's easier to do. That's how it's going to work. Now, how are we going to pick our u? what are we going to pick for our u? Well, whatever we pick for our u, we're going to have to be able to do du, the derivative. So we're going to want something that's easy to do the derivative. Well, it turns out we can do the derivative about anything. So that's probably not the most important consideration. The more important consideration is, what are we going to do with the part that's dv? What did we say? We're going to do the antiderivative. Well, some stuff is really easy to do the antiderivative. E to the x. Really easy. Sine. Really easy. Some things are hard to do the antiderivative of. What about natural log x? Do we know the antiderivative of ln x? We know the derivative of ln x, but do we know the antiderivative of ln x? We do not. So we would not want a log function to be our dv at all.
Ever.
So if we see a log function, we better pick that as our u, because we do not want that to be our dv. Again, we can do the derivative of about anything. So u could probably be about anything. So this is what we pick for u is more about what we don't want to have for the dv. What else don't we know the antiderivative of? We don't know the antiderivative of arc sine and arc tangent and arc cosine, do we? We know the derivative of those, but we don't know the antiderivative of those. So our inverse trig functions, if we've got one of those in there, we do not want it to be a dv, so we better make it be a v. Okay? Now the rest of the different types of functions probably don't matter. Your algebra functions, like x squared, x cubed, we can do the derivative of those easy, we can do the antiderivative of those easy, so those could probably go either way. The trig functions, sine, cosine, those could probably go either way, probably don't matter. Okay? And then the exponential functions, those are really easy to do the antiderivative of because they just are the same thing. So put those at the end. Okay, so this little thing, we're going to pronounce that liate. Liate. This is how we're going to decide which part is going to be our u. If you got a log function, that for sure needs to be your u. So whichever one comes first in there is the one you're going to pick. So these are log functions. These are your inverse, these are your inverse trig functions. These are your algebra functions like your x squared, your powers. These are going to be your basic trig functions like sine, cosine, tangent. And then these are going to be your exponentials like e to the x or 2 to the x or whatever. And that's going to be kind of a little friendly reminder for us of how we're going to pick those. Now, what does a integration by parts problem look like? Typically, integration by parts problems are a mixture of function families, the power rules, x squareds, x cubes, stuff like that. Algebra, those are typically called algebraic functions. Okay. Logs and trigs and exponentials are not typically functions. The name for them is actually transcendental functions. It's like e to the x logs. So integration by parts is usually used when you have a mixture of function families. Now, here's what I mean by that. If you look back at our u substitution problem, typically in a u substitution problem, it's either all trig functions or it's all kind of algebraic type functions. Now, sometimes right there, just algebra, powers, right? It's not typically a mixture of different function families. So the ones that we're going to have that are going to be integration by parts are usually going to look like this. X e to the x. E to the x sine x. X squared ln x. Ln x times cosine x. Something like that. They're going to be pretty simple, and they're going to be usually multiplication. And you notice that none of those really have any inside to them, right? So you wouldn't really think u substitution on any of those, because there isn't really anything on the inside that you would pick u to be. Unless you said let u equal x, but we talked about that yesterday. You wouldn't ever want to let u equal x, because then it's the same thing. Now, in this integration by parts, we might end up with UBX, but that's different. Okay? So that's typically that's one of the ways you're going to tell. The other way you're going to tell if it's integration by parts is none of the other stuff works. It's not a basic one. There's no, like I said, nothing on the inside where you could pick a U and then have a DU. So the only thing you got left is integration by parts. Okay? All right, let's look at a couple of examples here. So, I got two different problems here, and I've picked these two because they look very similar. Right? They both have a very, very similar look to them. And these are both a mixture. This is a mixture. It's got an algebra and kind of an exponential. Now, what would be the first thing to strike you about the one on the left?
E raised to the x.
What about it? How could you use that in working this problem?
Well, if you did the one on the left, e to the x squared, you can use the u substitution x squared, and you get x dx.
Right. That's the thought process I want everybody to have. Now, probably most of you were not thinking of that because right now you're kind of laser focused on this new thing and you're figuring, well, this must be the new thing. This must be the integration by parts. It's not. I'm pointing these out to show you that this one over here, yes, is going to be integration by parts. This one, however, which looks very similar, is going to be a U substitution. And so I want you to be able to look at these two, and so if this was a gateway test, I'd want your thought process to be where you could figure that out pretty quickly. And again, the key is this has some stuff on the inside. When there's some stuff on the inside, your first thought should usually be U substitution. So you're going to let U equal x squared. Then the du is going to be 2x, exactly what Joe said. The du is going to be 2x dx, which you've got an x dx setting right there. So this is tailor-made for U substitution. We're going to divide that 2 over. Tailor-made. Okay? So x dx is 1 half du. And then this is just going to be e to the u. Antiderivative of e to the u is e to the u. So that's going to be e to the x squared plus c. Right? And that is just what I would consider at this point in time just a pretty routine U substitution. Now, made a little more difficult because we now got this new one that we're talking about, and so you've got to be able to distinguish. But why is a U substitution what it is? It's because you can pick a U, usually the inside, the du sitting right there, it's all good to go. But this one is not, because what could you possibly pick for U? Yeah, the only thing on the inside of anything is x, and we already said that would be awful, because then your du would be dx, and all you would get is u, e to the u, du, and it's exactly the same thing, just with different letters.
Try to pick e to the x.
It would be awful. We let u equal e to the x, and du would be e to the x dx, which I guess you could say, well, that's just that. So that would be du, and then you got an extra x. What do you do with an extra x? You use this one to solve, which we could. X would be ln u. So for the x, you put in ln u. But that was one we said we don't know the antiderivative of ln u, right?
You could do it. I just said
no, yeah, it's a thought. So again, you got several forks in the road. You don't know where they lead, so you take one. Sometimes you got to turn around and come back.
So
right?
Why don't you just tell us the derivative?
The antiderivative?
Yeah.
It's actually one we're going to do in homework here because the way to do the remember with tangent, the way to do the antiderivative tangent was U substitution turned out, sine over cosine. The way to do the antiderivative of natural log is actually integration by parts. So I think that might be a homework problem or one we're going to do Monday or Tuesday. So we will talk about that. And then you could, you're right, then you could memorize it, and it turns out it could possibly work there. All right, so anyway, this one is, if you look at what I wrote here, this is definitely one, matter of fact, I wrote this one. This is one where integration by parts would work. It's a mixture of function families. So we look at our Liate. So here's how this works. So here's how integration by parts works. we have to pick a u, right? Remember on our formula here, our formula, we want our original integral to be in two parts. We want one part to be the u, the other part, the rest of it is the dv. We have to decide what to pick for the u. Well, what we pick for the u is going to be determined by Liate. So, we got an algebra and we got an exponential. Which one do we want to pick for our u? Algebra comes before exponential in Liate. So we're going to let u equal x. Now here's how I would write this. Well, here's how for years I wrote this, but then somebody made a suggestion last year, which I thought was a great suggestion. Here's how I've always done it, is I always did, and most books do it. I would write the u here and the dv here, right? Because remember, what we're trying to do is we're trying to break our original integral into those two parts, u and dv. Okay? So if I'm going to pick the u to be x, the dv has to be the rest, which would be e to the x dx. Now remember, the dx always has to go with the dv. Okay, the dx always goes with the dv. All right, so then your next thing to do is to do du, right? So you got your u, so we want to do du, which would be 1 dx, right? So I usually don't write the 1, we'll just write dx. And then what's the v? Now remember, v is the antiderivative. Now somebody last year, I did this for 20 years and never came up, but somebody said they would rather write the dv down here because it felt more like an antiderivative when you went up. Because like our chart, we go f, f prime, f double prime, and if you go up, it's antiderivative. Never dawned on me that that would even be something they would think about, but it kind of makes sense. So when they wrote theirs down, they always wrote u here, and then they wrote dv down here. So I don't care. It doesn't matter. We got to have all four of them here. So v is going to be the antiderivative, which would be e to the x. Now when we do that antiderivative, we don't need a plus c because we'll put that on at the end. And the dx, what happens to that? It just goes away because we're doing the antiderivative with respect to x. That's just e to the x, so it just goes away. Okay? So, you got this. Now we do our formula. The formula is uv minus the integral of v du. You just have to memorize that. So u times v would be x times e to the x minus the integral of v, which is e to the x, du, which is just dx. And so it accomplished what we wanted. We traded in for a new integral that's easier to do. And so we got x e to the x minus the antiderivative of that, which is e to the x plus c. Okay, now we can always check by doing a derivative. When we do the derivative of this, we need what? Product rule. So derivative of x is 1, e to the x left alone, plus x left alone, derivative of e to the x, minus derivative of e to the x is e to the x, derivative of c goes away, e to the x is canceled. There it is. Okay? So, but how else would you get that, right? How else would you have known that's what it ends up being? So there's your antiderivative of x e to the x.
So will you almost like never, like will you barely ever pick an exponential for your u?
Never hardly pick an exponential for your u because it's so easy to do the antiderivative. So usually it's one of these first three. Now sometimes you get a trig and an exponential together, right? But you would still pick the u as your trig. Okay, I think you have one of those in homework. Something kind of weird happens there, and we'll talk about that when we actually on Monday. Okay, let's do a couple more because there are some other things that can happen here. So that was a pretty basic one there. Okay, so let's go through the whole thought process now. First thought is basic antiderivative, certainly not, because it's two things multiplied together. The other thing we have is u substitution, which is where you're looking for something on the inside. There really is no inside of anything to do. It's a mixture of function families, which we broke down is a lot of times a hint that it's an integration by parts thing. Okay, so therefore we're going to pick a u, and that's going to be which one? Liate, log, of course. Fantastic job. And then if we want to do what was a suggestion last year, I'll put my dv down here. So the dv is everything else. So that's x squared dx. Now I will make a comment here, because this happens, where let's say you had a 3 here, or maybe you had a 3 in front of this, and when you do your du, you get a 3 there, and a lot of times we've divided that over. When we did u substitution, we divide that over the other side. You're never going to do that in integration by parts, because you're always substituting in your u, your du, your v, your dv, just as they are. So you're never going to be dividing things over on this side over here, okay, just as a point. Okay, so du would be 1 over x dx, and your v, 1/3 x cubed, and we don't need the plus c, okay? And again, I do like that. I do like that the thought of going up like that, I think maybe is a way of thinking of antiderivative more. So, because that is a mistake I would see people make. On their dv, when they went from dv to v, they would do the derivative then and put a 2x instead of doing the antiderivative. So that's key. All right, so the formula is u times v. So I would probably put the v first in this case. 1/3 x cubed times ln x. So that's u times v. Minus the integral of v du. Right? V du. Now, maybe you could have just simplified that in your head. That just simplifies to 1/3, which I could put out in front, and then x squared in here, right? Now I need to do the antiderivative of that. So that ends up being 1/9, because you're going to, antiderivative of x squared is going to be 1/3 x. And again, it accomplished what we wanted. We got a nice, easy antiderivative to do. So that's 1/3 x cubed with another 1/3, so that's 1/9 x cubed plus c, and then you can't, and being neat with your work's really critical, because you can't forget, it's easy to sometimes forget about this stuff at the beginning, the uv stuff. The other thing some people have asked me is, with the minus, do you need to do minus c here? No, because it's just a constant. Arbitrary constant can be positive, negative, whatever, it doesn't matter. So we don't have to write minus c. If you did, it'd be okay. But usually just put plus. Okay? So there's that one. Now we can do a product rule on this. We can check it all out. It's gonna simplify down to that when we do our derivatives. Okay? So those are two just kind of basic integration by parts. Depending how many there are, you're gonna for sure have 1 to 2 of those. Now there are some interesting things then that can happen with integration by parts. Okay? A couple of them. And so let's look at, well, there's a couple of them that I may put on the gateway test, and there's another one that I for sure won't put on the gateway test. We'll talk about that on Monday. Okay, so one of them is going to happen in this problem. So let's try this one. Okay, now remember, arctangent is one of those, that's why I was really up front in Liate, is we don't have a rule for the antiderivative of arctangent. Now, once we do it here, if you want to memorize it, go for it, but I don't think you're going to want it when you see it. Okay? But, so the antiderivative of arctangent. So we got to split this into parts. So one part is the u. So Liate would tell us we probably want that as that inverse trig, we want that as our u. We do not want that as our dv, because we had to do the antiderivative. We knew how to do the antiderivative of arctangent. We would just do it. We'd be done.
dv is just
so it's going to have to be arctangent. And so the dv is whatever's left, which is just dx.
that means
Okay.
v is u.
So the v would be, because it's with respect to x. So the antiderivative of 1, basically, with respect to x, is just x. Again, we don't need the plus c, because we'll be putting that in later at the end. Okay, now what's the du? 1 over,
Square root of 1 plus
not square root, not arctangent. Arcsine is square root.
1 plus
So 1 over 1 plus x squared dx. Now, somebody in the other class, right before we did this one, had asked this question, and nobody in here did, but some of you may have been thinking about it. Remember, the point of these is to turn our integral into a new integral that is simpler, hopefully. That's the best scenario. Or at least turn it into an integral that we can do somehow. Right? So doesn't it make sense that it's possible doesn't it make sense that when we do one of these techniques and it gives us a new integral, isn't it possible that that new integral will need to be done by one of the other techniques? Emily, quit shaking your head no. Has to be done by one of the other techniques. Now, we hope, and most of the time it's true, that when we use one of these techniques, our new integral is just a basic integral where we can just do the antiderivative. So most of the time that's what's going to happen. Okay? Well,
Not gonna be able to get away with this, right?
no, I said this could be. Okay? So, let's follow our formula. Follow our formula. You guys are so smart. You definitely deserve it. All right. Do you need this? I would feel like I'm cheating you if I don't challenge you by doing this. Okay? I know you'll say that because you don't want to look, bad in front of your classmates, but I know you're thinking different. All right, now, you don't want to be that person that says, yeah, make me do the harder ones. But I know deep inside you're all thinking. All right, so u times v, because I can show you the emails. I don't want to rat anybody out, but those emails I've got said, Mr. Clark, you're not challenging. All right, so u times v minus the integral of v du. So when we multiply x times this, I would just put the x on top. 1 plus x squared dx. So that's v du, right? Well, what do you notice here?
I don't want to.
Come on now, hang in there. I know it's Friday. We only got 20 minutes
Use
left. Come on.
substitution for an x squared.
Hang in there. We're going to, for a what?
1 plus
For the bottom. Now, hang on. There's a little bit of an issue with doing u substitution when we've already used u for something else. Now, you can do it because we're done with them. I mean, we're done with these up here. So you can do it now and it'd be a different u, but that does sometimes run into trouble. So,
Let's
what,
use y.
what you usually see them, what you usually see them use is w, right? Because, well, it makes sense. It's the second time we've used u. Double U. So yes. So W, and there's a little bonus here in a second you're going to see. So W would be 1 plus x squared. So the next thing we do is DW.
That's the one from Arthur.
From Arthur. Exactly.
I love that show.
That's a great show. All right. So DW. So see how fun calculus is? All right, so dw is 2x dx. Actually, on one of the websites I've got for you that's got some other practice, they actually, in all their u substitutions, they use w. I'm not quite sure why, but so you'll see that sometimes. Because it's a double u. So it's got to be better than just a single u, right? All right. So, this would all be fine if I still remember u substitution. All right, so x dx is 1/2 dw, and then the bottom is just 1 over u, or no, w, 1 over w. Okay, so the bottom is w, so that's ln, so 1/2 ln w. Don't forget the bars. And now it's minus, so the final answer, you can't forget to go back and grab the first piece. So x arctan minus 1/2 ln, and in place of the w, I'll put 1 plus x squared, but isn't this the one we said we didn't need the brackets actually, or the bars?
Well, you said it's okay if we.
But it's okay if you put them. So actually in your calculator, you probably wouldn't have them.
Plus, you try to memorize that.
And yeah, and like I said, just if you want to memorize the antiderivative arctangent, go for it.
So the antiderivative of arctangent is arctangent with other stuff.
Well, yeah, it's in there. Right.
Well, that's not.
Well, that's not nearly as cool as the antiderivative e to the x is just e to the x. But yes. Okay? So,
So what do we answer to that?
what's that?
That's not
Up there in the red. Okay? Yeah, wait, we're not done. It gets better. One last one. What's that?
But wait, there's more.
That one, that.
Wow. It's possible this doesn't even have an antiderivative because I look at this piece right here and I'm not sure this even has an antiderivative right here. Remember, the thing with antiderivatives is there are a lot of functions that do not have antiderivatives. Now, when we say don't have antiderivatives, we mean closed form antiderivatives. They're graphs. You can always kind of graph an antiderivative, right, using the idea of slope and stuff like that. But there might not be a closed form equation that actually gives you that graph, or that actually gives you that. And I think on this one, I don't think there would be. Right here, looking at this, because of that 1 plus x squared that's on the inside, with nothing else out here that would be the derivative of the inside, like we would get in a u substitution, I don't think there is. Matter of fact, Matthias, it'd be good to do it on your calculator. Are you doing that?
Yeah.
Yeah, just type that part, ln of 1 plus x squared, and see if there's an antiderivative.
So you're saying.
If it just spits it back out to you, at least the calculator is saying there is no antiderivative.
False.
So it's pretty easy to write functions that do not have an antiderivative, right? Okay.
Yeah. I'm just gonna say everyone's thinking, I don't feel challenged yet, so.
Next one, here we go. All right, let's finish with a bang then. All right, here we go. Okay. Thanks, Bodie. Every class needs one of those. Somebody that will step up to the plate.
The hero that algorithm.
No, it's not.
This is an algorithm.
All you do is look at it, relax.
This is actually good. This is good to do on a Friday right at the end because you need some recovery. You need some recovery time. You need a rest.
Like a week.
I wish it was
You need like a week. Actually, for you guys, it'd be 2 days because I know any homework I give you is not getting done until about 11 o'clock Sunday night anyway. So.
Hey, I have first
Or Monday first class. Yeah. Monday first class. All right. College will not be this easy.
You're right, it'll be easier.
It will be only because it's easier in college.
No.
Only
Probably
because.
that's right.
Well, Jesse said he went and.
Yes, you already know.
All right.
Jesse said he went and dropped out of
All right. So, let's finish this. So, again, not a basic one. It's a mixture of two different function families. And there's no inside. There's nothing you could let u equal to be an inside. So it's got to be integration by parts. So u is going to be the algebra,
Great job, Spencer.
right? The dv is going to be the e to the x dx, right? All right. So du,
That's it, right? 2x dx.
2x dx.
Heck yeah.
And the v,
EDX.
e to the x, which is, of course, why we wanted that to be the dv. All right? So, u times v, so x squared e to the x,
Wait, is this, we're gonna have to do two integration by parts in the same one? You gotta be kidding me.
minus,
No.
minus, in their face.
I'm just,
Minus.
I'm grabbing the answer.
Now look, here's this part I was talking about. Right here, We are kind of used to use substitution when we have this 2x. A lot of times we don't need that 2, so we divide it over. We can't do that here because remember what we're doing is plugging into a formula, and we're plugging in here the integral of v du. So we want all of du to stay over here. So we do not divide that over. Sometimes people are tempted to do that because we do it so much in u substitution. Okay, so it's got to stay there. So v would be e to the x, and then the du. So I would probably put that 2 on the outside, and then the x, and then the e to the x. It doesn't matter what order you write them, but that's what I'm used to seeing. And as I'm excited that you were looking ahead enough, you saw that, and you recognized it because that's right. X e that's now.
Now we can just pull an
Now-
answer from the one we already
I know
did.
you're not happy with me, but now I think I'm going to make you happy with it. Well, maybe you guys are hard to predict. But look what happened. We had an x squared, and then we got an x. Right? So what if, and so we're going to have to do it again. So what if this would have been x to the 7th?
We would have to do
Yeah.
it 7
I
times.
would have left it as. Do it 7 times.
Because now you would have 7x to the 6th here. And then you do it again, and you get x to the 5th, and do it again, you get x to the 4th. You have to do it 7 times. So I'm going to promise to you here and now that I will not, on the gateway test, make you do it more than 7 times. I promise you, you will not have to do it more than 7 times. Yes.
If you look at it, there's a pattern though. Wouldn't it just be x squared e to the x, and if it was x, would it be x? If it was x to the 7th e to the x to start off, it would go x to the 7th e to the x minus 7 x to the 6th e to the x and minus 5 all the way down to where you get.
No, but that, I think that 7 would still be in there, so when you multiplied by the 6, when you brought the 6 down, I think you'd get like a 42, right? Because you would have, you know what I mean? I think those constants would keep piling up. But we are right back to this one, right?
Yeah.
We are right back to this one. Now, here, it's totally up to you. I think, let me have your attention for a second. If we go to do this now a second time, which is exactly what needs to happen, usually we go ahead and use U and V again. Now we could use W. I mean, we're done with the U and V, but then you'd need, yeah, W and then I don't know what else. Z maybe or something. So usually we just go ahead and use U again. So U would be the X,
I used double V on the gateway.
double V.
Which looks exactly like
Yeah.
That's kind of a double U, but I don't know. I guess you maybe could. So just to run through it real quick. Here, but there is something you do have to be careful of here, and that is the distributing of the minus. We said it. We said it didn't matter on the plus C, but it is going to matter here. So when we do this in red, so being organized with your work, because it could happen. I'm not saying it's going to on the gateway test, but it could, especially in one of the earlier gateways. But U times V, so that's x e to the x, minus the integral of V du, which is just e to the x dx, which we expected. That's just going to be e to the x. But now putting together all those minuses and making sure we distribute them is a key. So final answer, x squared e to the x, minus, and this 2 has to go on that one, and then the minus, and the minus would make plus 2e to the x, and then the plus c, you just throw on e. So there is kind of a pattern, like Joe said. I'd have to work out a few to see exactly what it would look like, but like I said, you will definitely not have to do more than 7.
How would we just make one of them?
And figure it out, so we one of them down.
Like Bodie asks for the challenge, so maybe we should have.
Yeah, well, I'm still not challenged.
Do like an X to like the 30th and have them go all the way.
Yeah, I'll write it down.
Alright, so,
Thanks, everybody.
I would say like that'd be like a minus.
okay, here's the plan then. So this is actually in chapter 8. So in this book, different calc books organize these differently, and different colleges will study these techniques. usually these techniques are kind of in the break point between algebra 2 and, or algebra 2, calc 1 and calc 2. Okay, yeah. So most calc 1 classes will do, I think most calc 1 classes do integration by parts probably, but sometimes it's safer calc 2. And then we're going to be getting into applications of integrals and stuff, and usually in calc classes they do just more basic antiderivatives with those, and then they get into the harder partial fractions, trig substitution. They save that kind of for later. So that's why this is in chapter 8, so we kind of jumped to chapter 8 for this one section. So those are a few integration by parts problems. The LH packet, that new one I gave you yesterday, has got the second page is page 341. Now, the reason that those are so far apart in that book is that book does algebraic type functions in one chapter, and then it does exponentials in another chapter, and it does trig in another chapter. The old style books used to do that. So that's why they're spread out a little bit. So I think this page is more trig stuff. 341, I think 356 is some exponential. Now, couple more things here though. So 5.4, that's in the book. Just do a bunch more of them. Just go through and look for ones that look like you might, especially pick ones that look like something that it'd be challenging that you're not sure what road to go down, and try it and see, and then we can talk about it. Okay, now the last thing that I will show you, and this will be more for next week, there are a couple of websites like there were with the derivative. If you go on our class website, down here to the web links, down the far bottom left here, there are two links here I want to show you. Okay, there's this one that says derivative and antiderivative practice. Okay, now this is from this Jacksonville University in Florida, I believe. Now, if you go on this page, it's got Math 140, which is Calc 1, so those are the derivative ones. Math 41 is Calc 2, because most of these places will do their gateway test on antiderivatives in Calc 2 when they've done all of the different things. So you do have to be careful that there might be some on there that are techniques we haven't learned. So if I open up this, now all 8 of these tests are pretty much the same. And so I'll show you one here. It's got 8 questions. The nice thing about this is it forces you to look at them and try to recognize if it's one you can do or not do. One here is a basic, just very simple antiderivative. This is going to be a U substitution with the bottom, but it's also a definite integral, so it's a good chance to practice that because we haven't done many of those. Okay, but that's just that f of b minus f of a thing. Here's a pretty basic one, but it's got an e in it. Number 4, and it'll be this way in every one of these. Number 4 is one we don't know how to do. Now, you could look at it and should be able to figure it out because there's no good U substitution. It doesn't look like they're integration by parts. The other way you'd be able to tell is you go to the solution page, and as soon as you look at the solution to number 4, you see this a over x and b and all this stuff that's nothing we've ever done. This is the method of partial fractions. Okay? So that's definitely one we can't do. Then there's another one that's just a basic one, and then number 6 on all these is always going to be an integration by parts. Notice it's got an x and a cosine. It's a mixture, doesn't have anything on the inside, so it's a good place to get an integration by parts practice. Here you got one that's another U substitution, and then another U substitution down here. So this is a pretty good website. The other website down here at the bottom says antiderivative practice. There's a bunch of different links. The only 2 links I've been to that would really be worthwhile is right here. It talks about integration by parts. So there's a link right there.
And VisCal.
And you can go to that one, but that's not any good. Right here, it talks about substitution. So integration by parts and substitution. Okay, now you can look around some of those other ones, but okay. So there's a couple of links with some other practice opportunities. trying to think if this will be our last grade this term. I don't think so. We still have 3 weeks, right, after this week?
We're on a homework.
I think we have 3 weeks on this term, so,
Throwing some free points.
okay. I think we are gonna have, I think our last quiz of this term, if I'm not mistaken, I think it's on Monday,
And it's a joke. You're
the
just-
13th of March. I think it's Monday, the 13th of March is our
So we
last
only have
quiz
to
for this
get
term.
Gateway test and then that.
It's Monday, the 13th of March.
So we only have 2 tests left before the end of the year.
Right. For some reason that rings a bell, Monday, the 13th of March. What is that?
It's not.
That's our quiz. Oh yeah, that's the day after prom. So that's our last quiz of the term is Monday, the 13th.
Wait, did they move prom officially to the Sunday?
No, it's gonna make.
I don't think they have officially, but if they do, we're gonna have a quiz on that day, on Monday.
I'm just letting you know, if there is prom Sunday, I will not be in class. If there is prom Saturday, it's fine.
50 bonus points for everybody who's here the day after prom.
You got it, I'm here. I'll take a 3-hour count class. I can come in, not study for the test, not even answer any of the questions. You put the 50 bonus points on there, and I still have 50 extra bonus points left over for I would come and just
Get
sit.
0 out of 30.
Yeah, I would just come sit in class and leave, not go to the class.
No sleep. If you sleep, if you fall asleep at all, if you even nod up, you lose 20 points. No bonus points, and I take 20 points off your last quiz.
Oh, I can do this. If you give us 50 bonus points.